right? And so the easiest way to do that is to remember that this power series representation is true at least on this interval, but particularly at the center point, so at x not equal to 0. And what we can do is plug into our power series then, and we can write f of 0, right, is equal to log of 5 minus 0, which is just ln of 5, which equals c plus the sum, n goes from 0 to infinity, negative 1 over 5 to the n plus 1 times n plus 1, all times 0 to the n plus 1. Well, what happens with this term? This term is 0, right? Just add up a bunch of zeros, you get 0. And so what we learn then is that the constant, the unknown constant in our integral is not really unknown at all, because our integral is giving us a known function, right? It's giving us back a known function. So our power series then for f of x is equal to, or again, let's write down what our f of x is. The log of 5 minus x. This is equal to the value of the log of 5, natural log of 5, plus the rest of the power series, which starts at n equals 0 to infinity, negative 1 over n plus 1 times 5 to the n plus 1, x to the n plus 1. And at this point, you might see that these powers, all of these n plus 1s show up as n plus 1s, right? And so we could make a shift here, and we can change this so that this starts at n equals 1, and our power series then might look like ln of 5 minus x equals log of 5 plus the sum, n goes from 1 to infinity, negative 1 over n times 5 to the n, x to the n. Okay? And so there's our power series, and this converges, by the way. We need to check the interval of convergence, okay? But this converges on at least the interval, the same interval that we got it from. So it converges on at least the interval where x is between negative 5 and 5. Okay, and we need to check and see, does it converge at the endpoints or not? So we need to check the two endpoints. Now, just as a note here, when you take a derivative, you can never improve the interval, okay? You cannot add the endpoints, but we actually took an integral to build this series, right? We started with a geometric series, and we integrated it. Right here at this step, we integrated it. When you integrate, you can potentially make things nicer. So you can include endpoints that may not have been there before. So we need to check them, in other words, right? So on one hand, log of 5, we know 5 can't be part of the answer, right? Because log of 5 minus 5 over here does not exist. So on one hand, when x equals 5, ln of 5 minus 5, which is ln of 0, right? This is undefined. And if the function itself is undefined, then the power series is not equal to the function, right? So we don't need to do anything else with that one. We'll put a little x there. That one's not in the domain. But what we do need to check is when x equals negative 5. Okay, because log of 10 does make sense. So log of 5 minus negative 5, this does make sense. This is log of 10. All right, and so what we want to know is really, we're not concerned with like comparing with this number. What we want to know though is does this series converge when x is equal to a negative 5? So let's find out. So if we plug in here a negative 5, we have negative 1 over n times 5 to the n times negative 5 to the n, right? We've plugged in negative 5 for x. Goes in here, and then we just compare. So this is now the sum, n from 1 to infinity. This is now going to be negative 1 to the n plus 1. We've got negative 1 to the n and another one here, times 5 to the n upstairs, times n 5 to the n downstairs, right? These two cancel. And look what we're left with. We get at least a portion of our alternating harmonic series. The harmonic series itself we know is divergent, but the alternating harmonic series is convergent. Okay, so when x equals negative 5, this series converges, and what we learn then is that our interval of convergence is the interval, the half-open interval, from negative 5, open, can't be there because of the function itself, to positive 5, closed, converges. Okay, and the reason it converges there is because of the integral.